Hi, I'm Marilyn, and I'm here to talk about our work on the cost of suppressing volume for encrypted multimaps. And this is joint work with Megumi Ando from MITRE. A multimap is a data structure that maps labels to tuples of values, and a tuple can contain multiple values in it. A multimap supports get and put operations, where the get operation queries for a label and receives all the corresponding values for that label, and the put operation allows for the addition of new labels and values into the multimap. Multimaps are very versatile structures and are used for a variety of purposes, most commonly to create search indices and database indices. Structured encryption is a cryptographic primitive that allows a client to encrypt and upload a data structure to an untrusted server. In this talk, we will be talking about multimaps, and therefore the multimap will be the running example. Structured encryption also allows a client to later query for labels in this multimap using encrypted labels, which are also referred to as query tokens. And the client should receive, in response, the encrypted values that correspond to this label. The adversary, or the untrusted server, observes the execution of the structured encryption scheme and learns meaningful information both about the underlying multimap as well as the labels that are being queried. And this information is referred to as leakage. The quantification of leakage in structured encryption allows for flexible trade-offs between security and efficiency of structured encryption schemes. In particular, I would like to explain the indistinguishability definition for a leakage profile L for structured encryption. This definition is the one that we use in our paper and for our proofs. So first, the adversary selects two multimaps and sends them over to the challenger. The challenger chooses a bit and therefore one of these multimaps uniformly at random and encrypts the multimap and returns it to the adversary. Then the adversary selects two sets of queries, and under the condition that the leakage function evaluated on the first multimap and the first set of queries is equal to the leakage function evaluated on the second multimap and the second set of queries. And finally, the challenger sends back the encrypted queries or the tokens corresponding to the labels in the bth set. At the end of the game, the adversary tries to guess which multimap and set of queries were chosen. And the security requirement of this game is that the adversary not be able to guess with probability much greater than 1/2, which is the same as a random guess. To start with some background for our work, leakage profiles have been studied in many ways, and one of the lines of work tries to use leakage in order to infer more information about the underlying structure and queries than expected. And these attacks use either the query equality leakage or the volume leakage. And the query equality reveals whether two queries or two labels are equal to each other when they're queried. And the volume leakage reveals the number of encrypted values that correspond to a given query or an encrypted label. And there's been a line of work in looking to suppress the leakage patterns that are used for attacks. So for instance, ORAM can be used to suppress query equality, and there's ORAM-like techniques that can be used to suppress query equality from more complex data structures. However, we also know logarithmic lower bounds for communication complexity when the query equality leakage is suppressed. However, the overwhelming majority of attacks rely on the access pattern leakage, and in particular, query volumes, which is the number of encrypted values that correspond to a label. And so there is this line of work in volume hiding, which looks to suppress the query volumes. Naively, one could think of using padding to hide the query volume. So how would this work? For every label that can be queried in the multimap, you would add in empty values or garbage values so that whenever the label is queried, there would be extra values in that encrypted response, and therefore the true volume of that query would never be revealed. But it turns out that this solution is inefficient both in terms of storage as well as communication. And so in 2019, Kamara and Moataz proposed the first volume hiding scheme, which would reuse encrypted values. So use encrypted values from other responses instead of using only padding, and therefore hide the query volumes of the label that's being queried. And later in 2019, Patel, Pergiano, Yo, and Young proposed the formal definition of volume hiding and also introduced a second volume hiding scheme. In this work, the definition of volume hiding that we use is the one that was proposed in the Patel et al. Paper. There's also been a line of work in lower bounds, which looks to study the security and efficiency trade-offs. And however, most of this work has looked at leakage patterns that leak both the access pattern and the query equality. And we also know separate bounds for the query equality. So the question that we ask in this work is, what is the cost of hiding the query volumes in particular? And how much should we expect to pay if we do not want to reveal query volumes? So we define in particular this leakage profile that we refer to as minimally leaking. And what we mean by minimally leaking is that the leakage of the scheme is no more than the total size of the multimap, which is n, which is the number of values that are present in this multimap, and the query equality, which is the whether two queried labels are the same. So given this minimal leakage profile, we ask, what are the costs of having a scheme that has only this leakage? So the first thing we see from this definition is that in order to suppress the volume of a query, you have to read, the scheme has to read at least the maximum number of encrypted values. So at least the maximum length has to be read. And then what we show for our first bound is that if you want optimal read efficiency, where read efficiency is the number of values that must be read. So given that you have to read the maximum number of values, if you were reading exactly the maximum number of values, what we show is that each of the tuples in the multimap will have to be padded. So there has to be pretty much the naive solutions amount of padding in order to have a scheme that is both optimally read efficient as well as minimally leaking. And then we go on further to show that if you use parts of other responses instead of padding, these parts of the other responses cannot be sampled completely at random because that cannot give minimally leaking. So we're now relaxing the read efficiency a little bit. So we're allowing for a constant number of values to be read, which is greater than the maximum length. So earlier, our results said exactly the maximum length of values has to be read. And now we're allowing for more than that to be read. And say for a concrete example, we allow the scheme to read 10 values for every query, when the maximum length in the multimap is only 5. And let there be two encrypted responses such that the real lengths of both of those responses are 5 each. So 5 values corresponding to each of the labels. So as an example, you have CI, which has 5 real values that should be retrieved. And then you want to add 5 more because the scheme has to read 10 values. And these 5 values are picked at random from the remaining encrypted values. And then we look at a second response, CJ, which also has 5 real values that have to be read, and then 5 values which have to be sampled from the remaining values. Now, what we notice in particular is that the server can observe the overlaps between these two encrypted responses. And it can look in particular at the size of the overlaps or the number of encrypted values that are in common between these two encrypted responses. And to think about a different example, so if CI and CJ were much shorter than the maximum length, so say CI and CJ only had 1 value each, the essence of our proof is that we show that shorter responses tend to have larger overlaps. So the size of the overlap depends on the length of the true response, and therefore it reveals some information about the volumes. And this is our main result in the standard model. However, the standard model might be too restrictive in that it gives the adversary a lot of power. So going back to the definition of minimally leaking, we see that the adversary is allowed to choose all of the labels that are queried in the query phase. What if the adversary was not given this power? So we propose a new definition that allows for a weaker adversary model where the adversary no longer chooses the queries. Instead, the challenger samples queries from a distribution D, and this distribution is used to create the encrypted tokens that are later sent over to the adversary. In particular, this distribution is public and known both to the adversary and the challenger. And our definition is inspired by the attack paper literature, where the attacks often assume that the adversary knows a distribution and the queries are being sampled from that distribution, even if the attacker cannot choose the queries. And arguably, in some settings, it is more realistic to assume that the adversary cannot choose queries, but instead knows some information about the cumulative properties of the queries, like the distribution. And so we ask, can we do better in the sample minimally leaking setting? And we end up showing that it is possible to do better. And we have a scheme in the sample minimally leaking setting that shows that we can do better. And we show experimental evidence for this fact as well. So here's a summary of all of our results. Please read our paper if you're more interested, and I can take any questions. Thank you.